Okay. Can everyone hear me? Write a yes or no. I mean, write yes on the chat. All right. Thank you, Shubham. All right. So, welcome to the second day of this webinar. Pritam, are you there?
Yes, yes, yes.
All right. So, we will not wait too long. So, those of you who have
Mhm.
attended yesterday, welcome back. And those of you who are new today, you might find it a bit hard to catch up. But then we'll be uploading the videos hopefully by the end of today. So, without waiting anymore, without further ado, let us start today's webinar. All right. So, Pritam, I'm handing over to you.
Thank you. Okay, so welcome again, guys. Mm, so today's webinar talk, like I'll show you some of the other advanced kind of NLP stuff, which are based on word embeddings and stuff like that, and recent NLP advancements and stuff like that. So I'll just go and present. Also, I have two notebooks for today's webinar. I'll just show you the notebooks and then I'll give you the notebooks for you guys to try out, just like yesterday. Okay. Okay. So can you guys see the screen? Okay. That's a word embeddings. So what exactly are word embeddings? So it's a representation for text where words have the same meaning. I mean, those words that have the same meaning have a similar kind of representation. As suppose words such as cats, dogs, and other animals are similar because those are animals. So they will have a similar representation. That's a word embedding. That's just a basic definition. So actually, we have something known as vector space, word vector space, and those words are modeled in that vector space, and that's how we get the representation of words. So that's how we get word embeddings. There are a few kind of word embeddings, such as frequency-based word embeddings. Then we have prediction-based embeddings. So I'll start with frequency-based embeddings. So these are the kinds of frequency-based embeddings, such as count vectors, TF-IDF, co-occurrence matrix. Yesterday I talked about TF-IDF. Uh, so today we'll talk about co-occurrence matrix. So what exactly is co-occurrence matrix? So those words which I mean occur along with each other, it forms a co-occurrence matrix. So suppose we consider a corpus consisting of the following uh, sentences. A penny wise and a pound foolish. A penny saved is a penny earned. So how we will compute the co-occurrence matrix is we will take the count of the next word and the current word. Okay, then divide it. So it represents how many times the next word is following the current word. So suppose the word is a and the other word is penny. So how many times the word penny is followed by sorry, how many times the word penny is followed after a. Okay, so you can see here a penny. So two times, right? So two times penny is after a. Oh, sorry. Okay, so this is a co-occurrence matrix. So it The whole table, it shows that A is followed twice by penny, and the other words follow penny once in our corpus. So after penny, earned is there. You can see after penny, earned is there, saved is there, wise and foolish. So four words. Okay. Then we have prediction based embeddings. So these methods are prediction based in the sense that they provide probabilities to the words, and it proved to be the state of the art for tasks such as word analogies and word similarities. So state of the art means a very recent kind of thing, but this was the state of the art. Okay, it's not now a state of the art because it has changed. The recent trends have changed. Also, they were able to achieve tasks such as king minus man plus woman equals to queen. So this is actually a kind of thing like how can we relate a king and queen with man and woman. So if we take the word king and uh, subtract the word man and then add woman, then it becomes queen. So this is actually the word representation of king, word representation of man, woman, and queen. So after solving this equation, it was found that it equals to the word representation of queen. So this was very important that it showed that king, man, woman, queen, those are connected. Okay, because uh, uh, we have to find the word similarities. This is a model of this is a model, I mean language model, which is based on prediction based embeddings, which is word2vec. So word2vec was created by Google in 2013, and it is a deep learning based model which computes and generates high quality distributed and continuous dense vector representation of words. So it's a vector representation of words. So I think word2vec has a vector size of 300. So that's the size of vector in word2vec. So it captures the contextual and semantic similarity of words. Okay, so that king minus man plus woman equals to queen, those kind of things. These are unsupervised models. So if you know machine learning, there are supervised models and there are unsupervised models. So this word2vec is an unsupervised model which can take any kind of text and it can generate a word embedding for the words present in the text. So it can take massive textual corpus, I mean, create a vocabulary of the words and generate word embeddings for each word in the vector space representing the vocabulary. Okay, so the word2vec model is actually based on two algorithms. One is continuous bag of words and the other is skipgram. So we have learned about bag of words yesterday. Now this is a continuous bag of words model. We'll just see what is a continuous bag of words model. So it tries to predict the current target word based on the source of context words. Okay, so I'll just give a simple example, it will be clear. So if we have a sentence like the quick brown fox jumps over the lazy dog, and if we divide everything in this sentence in the pair of context window and target word, and considering a context window size of 2, so we will get examples such as quick fox brown. Okay, so this middle word, okay, so this is the middle word brown. Okay, this is the middle word. So this actually is the target word. Okay, so we have to find out this word based on the surrounding words, which is quick and fox. Similarly, for this pair, we have quick and the brown. Okay, so based on these two, we'll have to figure out the target word. Okay, so for this sentence, this is the pairs based on context window size 2. Okay, the model tries to predict the target word based on the context window words. So these are the context window words for the word brown and so on. Okay, we'll divide the whole sentence into such pairs. Now we can model this continuous bag of words as a deep learning classification model, which can take the context words as the input. Okay, so these are the context words, those are the input, and predicts the target word. Okay, these are the target words: brown, quick, lazy, and so on. How to implement the CBW model? So we build the corpus vocabulary. So corpus is the whole text. We build the vocabulary first, and then we build this generator. Okay, context and target, and then we build the model architecture, train the model, and then get the word embeddings. Okay, so for the corpus vocabulary, what we do is we extract out each unique word. Okay, every unique word from the vocabulary, and we assign a unique number for each of the word. After that, what we do is we build the generator of this context words and the target words. So since we have a length of 2, okay, window size is 2, the target word length is 1. Okay, so and surrounding context, those are the 2. Okay, 2 words, we are taking 2 words. So also we have to remove the stop words first. Okay, like if the text was something like in the beginning God created heaven and earth, then we'll remove all the stop words. In the and all these things will be removed, and so this will be the sentence. Okay, after removal of stop words. So if we're trying to figure out the uh, target word created, then the words which are near this created, God, heaven, beginning, earth. Okay, so if these words are given, then we have to figure out this word created. So this is the target word, and these other words are given. Okay, so the target word is created. So the inputs will be the context words. Okay, these are the context words: beginning, God, heaven, and earth. So these are context words. These are passed to an embedding layer, which is initialized with random weights. Okay, this may be a bit difficult, like the whole CBOW model and word to vec model. I'm just giving a brief overview of this stuff so that you can just know what exactly happens, and you can look up all those things, what exactly is CBOW if you're interested. So the like word embeddings are then propagated to a lambda layer to average out the word embeddings. Okay, so this is continuous bag of words because it doesn't consider the order or sequence in the context words when it's averaged. So it's similar to the bag of words model. Like yesterday I showed you, it doesn't consider the order or sequence of the words. Okay, this averaged sequence is then passed onto a dense softmax layer. Okay, so this is a kind of mathematical stuff. Softmax layer. It predicts the predicts the target word. Okay, and to rectify the errors, okay, to compute the loss and then back propagate the errors. Back propagation is done for neural networks to adjust the weights. Okay, the weights. These are the weights. Initialized random weights. So to adjust the weights, we compute loss and then back propagate. Okay, it then repeat the whole process for all the pairs of context and target words. Okay, so this is the architecture of continuous bag of words model. Okay, so the embedding layer, then lambda layer, then softmax layer, and then compute the loss and back propagation. Okay, so this computes the target words, bag of words, CBOW model. Then skipgram is the opposite of CBOW. It predicts the context words given the target word. Okay, so here target word is input while context words are the outputs. So it's opposite of CBOW algorithm. So if like the suppose this is the sentence and we have to figure out we have what will be the word here. So the cat blank on the mat. So the most probable will be sat, ran, late, stood. Okay, these are the words which will be more. I mean these are more eligible to be here based on the whole words. Okay, while these words are not that much eligible. Ate, drank, slept. Okay, so this is how the skip gram architecture works. I'm not going into the detail of skip gram architecture. This is another one. So this is GLOVE. Okay, GLOVE is global vectors for word representation. So it is also an unsupervised learning algorithm for obtaining vector representations for words. So it's similar to word to vec, but there's a difference that unlike word to vec, GLOVE does not rely on local statistics. Okay, local context information of words. So it incorporates global statistics. So global statistics means GLOVE is trained on some huge data which is used globally, which can be used globally. While for word to vec, you have to train a particular corpus which is only for the local, which is based only on the local statistics. Okay, so I'm not going into details of all these language models because this will be a very advanced kind of thing. I'm just giving an overview, like what exactly is done right now, because we have learned that from yesterday's talk that bag of words representation or TF-IDF, it doesn't give us much information. So word embedding models, vector models were developed for more understanding of the words. Okay, so how to get similar kind of words and stuff like that to get more information out of words. After GLOVE came BERT. Okay, so BERT is actually a very recent language model. It was published by researchers at Google AI Language in 2018. Okay, the full form is bidirectional encoder representations from transformers. So if you're interested in BERT, and before going into the details of BERT, you have to know what is transformers, what is attention mechanism. This transformers thing is built upon attention mechanism. Okay, so BERT is a language model. It's also an unsupervised language model. So it achieved state-of-the-art benchmarks across 11 tasks, okay, 11 NLP tasks, which included question answering, okay, based on this dataset, SQUAD dataset, which is Stanford question answering dataset, and MNLI, okay, natural language interface, and others. Okay. In total, 11 NLP tasks. It achieved the state-of-the-art benchmarks. Okay. It has been trained on a lot of words on the whole English Wikipedia, which consists of around these many million words. So it's the good thing about BERT is they have released all these pre-trained models of BERT so that anyone can use it without training again. Because training these many million words, it takes many hours, and we also need very high computing powered machines for this kind of training. So okay, so but it makes use of transformer, which is an attention mechanism that learns contextual relations between words in a text. Okay, so one advantage of BERT is it gives contextual information between words. So past language models such as these word2vec, GLOVE, it it built the context-free word embedding. So context means suppose we have a word such as apple. Okay, apple. If I write apple, then it can be the fruit apple or the organization apple. So the earlier models such as word2vec and glove2vec, glove, it couldn't differentiate between apple the fruit and apple the company. So, however, BERT, it can differentiate between apple the fruit and apple the company. So it provides context. Okay. So the other models, such as word to web or glove, it used to read the input in a left to right or right to left kind of approach. Okay. But BERT, what it does is it does the left to right as well as right to left at the same time. Okay. It reads the entire sequence of words at once. Okay. That's why it is considered bidirectional. So, because of this approach, like left to right and right to left at the same time, it can learn the context of the word based on the surroundings. Okay, this is just a brief overview of BERT. And BERT actually is being used it's been used in many tasks and many other BERT models, which is based on BERT, the pre-trained. So, what is a pre-trained model is like they train the whole model on a very large set of data, okay, such as a whole English Wikipedia or something like that. Okay? So those pre-trained models can then be used by others to uh, work upon. So based on BERT, many pre-trained models have been released for people across the world so that they can work upon this. And currently, Google is using the BERT model. Okay, not exactly the basic BERT model. They may have advanced a bit for their search, for their searching and stuff like that. So if you search in Google, now they are using something which is based on BERT. So even Facebook has released a pre-trained model based on BERT, and many other. Microsoft is also using such models. So yeah, so BERT is being used. The BERT model is being used everywhere across the world right now. So we'll see two examples which is based on BERT. Okay, one is sentimental analysis using the IMDb movie review dataset. Okay, and the other is summarization of text. So we'll see both of these notebooks which is based on BERT. So we'll first go for the sentiment analysis using IMDb movie review dataset. So I'll just okay, okay. Can you see this notebook? Can you guys see the notebook? Or
No, we can see the presentation, but not the notebook.
okay, I have to stop sharing then. I think it's visible now.
Yeah, it's visible now.
hmm So yeah, so this is a sentimental analysis of the IMDb movie reviews using BERT. So this IMDb movie review dataset is already available. You can download the whole dataset. It consists of around 25,000 movie reviews, okay, which are labeled properly as positive or negative, POS or NEG. Okay? Those are the labels. So for this, we are using K-train library, okay, which is Keras wrapper for training and deploying of neural networks. So first, this is just to install the K-train. So this is for Colab, we just use an exclamation before PIP. So after installing everything, I won't run this whole notebook again because actually the whole the whole learning thing, it takes around 2.5 hours. So yesterday I just ran and it went on for 2.5 hours. So this is After installation, you have to import Ktrain, and then from Ktrain you have to import text. Okay, this is for the version of Ktrain. You can check the version of Ktrain. After that, we'll extract the IMDb movie review dataset, which is stored here. Okay, this is the original dataset path. So after that, what we'll do is we will assign the whole file name. Okay, this is the file name. So we'll assign this to this path. Okay, for our local path. This is our local path. So after assigning this, we'll store the path here. Okay, this is the IMDb data dir. You can give any name. Then after that, what we'll do is we will use this function, the text from folder function, where we will pass the path, IMDb path, the maximum length. Okay, 500. This is the maximum vector length. Okay, 500. Then the pre-processing mode is BERT. We'll use BERT, and these are train test names, and the classes are POS and NEG. Okay, which is there in the dataset. POS means positive, NEG is negative. So after running this is train, validation, and this is pre-processing. You can give any name here. You just remember the name this one. You have to remember this. So after this, it will pre-process and train and do everything. So here, see, it will load the training validation data and then pre-process it according to BERT's requirement. Since we have given it BERT, okay, a mode is BERT. So it will do. Also, we are using uncased BERT model. Okay, this is the uncased version. So if you write lowercase or uppercase, it won't matter. This is uncased. Then, yeah. So after that, what we'll do is we'll load the BERT pre-trained BERT model. Okay. So text. This is the text classifier function from text, and then this is the this is the whole BERT model. Okay. After that, we'll use get learner, then pass this model. Okay, and pass on every other parameters. Okay, batch size is 6. After that, what we'll do is we'll train and fine tune the whole model on the data set. Okay, I have used 2 epochs here. You can give more epochs, but it will then take more time. So I've already done this yesterday. I won't do this again. After the learning and everything is done, you can use the learner. Then you can take the predict. Okay, you can assign any name here. So predictor is used to predict the whatever new you are giving. So it will predict whether it's a positive or negative review. Okay. So this predictor, it will take these parameters, learner model and pre-processing. Okay. After that, I took a few of these sentences, which are kind of reviews. Okay, movie reviews. So after you take all these movie reviews, you just pass on the data to the predictor dot predict function. Then it'll give the class names, okay, POS or NAG. As you can see, this was a negative comment, right? The movie was really bad. So these were just manually given randomly. I assigned this, okay. But these are taken from actual movie reviews of Terminator, Dark Fate, and Terminator Genesis. Okay, so these are actual reviews which are given by people. So as you can see, like they are being classified accordingly. So this is a very positive comment. So you can see it will give a very good result of classifying any movie review into positive or negative. Also, you can see the score, like validation accuracy is 94.4% using 2 epochs. But if you train for like 5 or 6, then it may increase also. So we can see that BERT achieves a very good validation accuracy. That's why it can, like, even if you give a whole long kind of movie review, then also it'll properly classify into positive or negative. Okay, you can try this whole notebook by increasing the epoch timings. I mean epochs. Also, make sure that the runtime. Okay, before running this, just change the runtime type to GPU. Otherwise, it will take a lot of time. So I'll share this with you all. You can try it out. So, and then you can also add some other movie reviews and then check if it's giving a good classification or not. So yeah, this is the IMDb movie review dataset classification, sentiment analysis. Okay, so positive or negative using BERT. Then yeah, okay. So that was the whole sentiment analysis using the IMDb movie review dataset. Now you can take other datasets also. So there are other datasets available. Then you can try out sentiment analysis for other datasets also, such as hotel review datasets. There are many review datasets you can find out in the net, such as Yelp or some other review datasets. So you can do sentiment analysis with very high accuracy using, but we have seen that. Then this is summarization of text. Suppose we have a big chunk of text and we want to summarize the whole text. Then you can also use BERT for that. Okay. Now, before going to summarization of text, I'll just show you what we'll be using in the summarization of text. So there's a particular algorithm which is known as text rank algorithm. Okay. So text rank is based on page rank. If you know page rank, like it's what Google was based upon in 1998. So page rank is named after Google's founder, I mean Larry Page. Okay, yeah. And there was another guy who was Sergey Brin. So Larry Page and Sergey, they came up with this algorithm, which they named PageRank. So it was very efficient, and that's how like Google was able to give out much more efficiently the websites that people were looking for. Okay, so it used to rank the web pages in online searches, PageRank. So that's an algorithm. TextRank is based on PageRank for extracting sentences a uh, from a piece of uh, corpus. Okay, so important those which are very important. So according to the algorithm, so that's TextRank. So yeah, this is how TextRank works. So we have some articles. We'll combine every article to a huge text. Okay. After that, we'll split the text into sentences. So yesterday I showed you the tokenization. Okay, sentence tokenization. So we'll use that. Then you can find out the vectors. Yeah, the word vectors, and from the word vectors, word embeddings. So we'll use word embeddings for this one. Then after we calculate the word embeddings, we kind of create a similarity matrix between the sentences. Okay, the embeddings of the sentences. Then after that, from the similarity matrix, we create a graph, and then using that graph, we rank the sentences, and then we'll get the summary. Okay, so this is how the whole pipeline is all about. I'll just show you the code of this kind of text summarization, which you can do with BERT. There's already a library in Gensim which has the text summarization already there. Not, but they're not using BERT, so I think they're using word-to-vec models for that. So you can also try out the Gensim library also for summarization, text summarization. It's also very good, but using BERT will get much more efficient and better results. So I'll just show you the notebook. So yeah, uh, for this notebook, I'll have to share the CSV file, CSV or Excel. I forgot the file. I just have to check. So it's in my drive. So for mounting from my drive, I'm using this piece of code. You can also store the file here. Okay, here, just drag and drop the file here, and then take the path name and then use that path name for the reading of the whole file from here. But it's in my drive, so I'll just use this code. Okay. So you'll get this code. You just copy it, paste here. Okay, so the whole drive is mounted here. So you can see this is my Google Drive. So you can mount the whole drive. From there, you can just go and look up where the file is present. Okay, then copy the path name. Let me first run this. This is just a NLTK library. So yeah, the path name for the file in my drive is this one. So for your purposes, you can also use Google Drive. Okay, this is the path. Okay, this is DF is data frame. Okay, PD is pandas. So we what I have done is I'm using pandas as PD. So I'm renaming pandas as PD. Otherwise, you have to use pandas here. Okay, I'm just using PD for short as a short form. So this is the data frame. So pandas.read CSV. So it's a CSV file, comma separated file. Okay. So it's reading the CSV file. And I'm using this encoding Unicode escape to escape the Unicode error. So after that, you will get this data frame, which has the whole file has uh, these columns, article ID. This is the title of the article. There's some text. So we can see the text. Okay. Article text. Okay. This is the column name. So we can just use the article text column name, and zero means it will give the text present here, and the zero. So this is the text present there. Okay. You can also write some other such as one, and it will give the text present in row one. Okay. So what we can do is we can either summarize each of the article individually, or we can generate a single summary for all the articles. Now what we'll do is we'll take all the articles and then generate a summary. So to take all the articles, what we'll do is we'll use this one. Okay, this is the code for taking all the articles. We are assigning a blank list. Then for all the sentences in this particular column, we are token. I mean, for all the paragraphs or text, okay, present in all the rows in this particular column. Okay, for all the rows in this particular column, we'll we'll divide it into sentences. Okay, so this is the sent tokenize that I showed you yesterday. So this will tokenize every sentence, I mean every text into sentences. Then we'll just flatten the list. Okay, so this will give the list. So you can check if you run this, then it will give you the five sentences present in this particular list. Okay? You can just see the sentences. If you just print sentences, then it will give the whole list of sentences. Okay, so this is the whole list of sentences. Okay, we don't need this now. Then This piece of code, what it will do is it will pre-process the sentences. Okay, this is pre-processing. So clean sentences. So it what it will take is take the sentences and then it will use this regular expression. Okay, it will replace anything which is not word with blank space. So this means word. Okay, these are the words. It may be uppercase or lowercase, A to Z or A to Z with blank space. Then what we'll do is we will convert this preprocessed text into lowercase. Okay, so this will give the lowercase for all the sentences. After that, we'll remove stop words from the this. Okay, we'll remove stop words. So this is the function for removal of stop words. After that, if they are not in stop words, those will be removed. Sorry, those will be kept and the stop words will be removed. So yeah, we'll finally get the clean sentences. So you can check how it looks using the print statement. We'll run this file, we'll run this cell. So yeah, so we'll use a version of BERT which is applied for sentences, okay, sentence similarities. So it has achieved state-of-the-art results for sentence embeddings, which is known as sentence BERT. Okay, there are other sentence embedding models such as Google's Universal Sentence Encoder or Facebook's InferSen, but sentence BERT achieves the state-of-the-art results. So we'll be using sentence BERT. So for sentence BERT, we have to install this particular library, sentence transformers. We'll just install it. You don't have to worry, it will install itself and build everything. Okay. After that, now this is the whole piece of code for getting the whole summary. Okay. So it may look a bit difficult kind of code, but actually it's easy if you look at it. So these are actually all the functions imported from the sentence transformers library. Okay. From the sentence transformer library, all these are imported. All right. Then the model. Okay, this is where everything is working on. So we'll use this particular pre-trained model which is already there in sentence transformer. Okay, we'll use this model. You just have to call the function name sentence transformer and pass the pre-trained model name. Then it will calculate. It will work upon this model. Okay. So after that, this model is used to encode the whole clean sentences. Okay, we got the clean sentences list and we'll encode all the sentences using this particular model. Okay, this is the function for that model.encode clean sentences. Very easy. Okay, then we'll get all the embedding sentence embeddings for all the sentences. After that, we'll assign a similarity matrix. Okay, with zeros. So first we'll fill the matrix with zeros and then use cosine similarity to fill the matrix with similarity scores. This is just assigning zeros for the similarity matrix. Okay. Then from sklearn library, we'll import this cosine similarity. Okay. This cosine similarity function, what it does is it calculates the cosine similarity between two variables. The cosine similarity means it's a similarity score. Okay, you can check up cosine similarity. Then for each sentence in this particular list, okay, for each sentence in this particular list, we'll find out the cosine similarity between the embeddings of that particular sentence with the other sentence. Okay, this is what similarity matrix IJ means. Finds out the cosine similarity between these sentences. First sentence, the second sentence, first sentence with third, and so on. Okay, it will find out cosine similarity for all the sentences. After that, after you find out this similarity matrix, it'll now we'll import this particular library, network X. Okay, this particular library is for PageRank implementation. So we'll take a variable name and then from network X, we'll use this function, pass on the similarity matrix to get the whole graph of the similarity matrix. Okay, this will transform the similarity matrix into the graph. After that, what we'll do is we'll calculate the page rank scores from this particular graph. Okay, scores. So we already have a function page rank. Just pass the graph. We'll get the scores. After that, to rank the sentences, we'll sort the scores according to a descending order. Okay, so this will sort everything in a descending order. Uh, so the highest rank will be at the top, and then so on. Okay? And we can extract top 10 sentences, or you can extract 20, 15, or 6, anything you want. So this will give the whole list of sentences. Okay, so I'll just show you how to run. So if you run this thing, it'll take some time to download the model. Now you can try with different models that are available in Sentence Transformer. So I'm using this one. You can use other models to check the whole thing. It will take a little bit of time. Okay, so it's a big pre-trained model. You can see from the size, it's 1.31 GB. So the codes may look difficult or dangerous at times, but it's easy if you work upon it for many days or many months. So you can also try out with some other similarity. I'm using cosine similarity. You can try out other similarity functions which is already there in sklearn. You can try out. So if you have any questions, you can ask in the meantime. Okay, before running all these notebooks, just make sure the runtime is on GPU. Also, you can use this piece of code for any text summarization. You just have to replace, if you are not using this particular CSV, you don't need to use this one. You can take any text, okay? Take any text, and then from that text, you can apply this, okay, for the whole text. Just first find out the tokenized sentences, and then store it in a list first, and then you can work on it. So yeah, so this is the whole output. You can change the output if you want. If I want 5 or something, you can just change here. Okay, so this will give you. And if you want the score also, then just remove the 1. If you like, say, rank sentences I, it will give the scores also, the text rank scores alongside. Okay, so that's how you can do sentence. summarization. Okay, text summarization using BERT. Okay, so I think that's the last slide for today. Yeah, that's the last slide. So anything that you want to ask anyone, anything? Okay, then I'll just stop the screen sharing. Okay, thank you. Thank you. Thank you. Yeah, thank you. Mhm.